Hi everybody, my name is Uzamaka Anyibana. You can call me Uzo, and today I'm going to be walking you through a very interesting topic in CS109, information theory. But first of all, I'm going to tell you a little bit about my day. So I live in Lagos, Nigeria, for context, and as of recent, it's been raining cats and dogs. And unfortunately, I got stuck under the rain today. I was so sad, and then I remembered that my mom said that she had something really important that she wanted to tell me. So to lift my spirits up a bit, I decided to call my mom. Now remember, there's low signal because of the rain, and there's a bit of static over the line. But I call and she picks up on the first few rings. I say hello, psh, static. Can you hear me? Psh, static. There's a lot of static over the line. It may seem a little vague right now, but that in situation on its own is information theory in action. At its core, information theory is the science that tries to measure how we represent, transmit, and understand messages, especially when they come from noisy backgrounds or over limited channels. So, we're trying to answer the question, what exactly is information? And I'm sure we all know information to be structured data or data that makes sense. That's its primary definition. But that doesn't really go when we're talking about information theory. When we talk about information in information theory, they say information reduces uncertainty. It reduces our level of assurance. It narrows down the number of given possibilities in a given question. Now, information theory is bordered on three core questions. The first one being, how much information is there? Second, how small can we make that information? And three, how can we send that information across accurately? In the 1940s, specifically 1948, Shannon Cloud, or Cloud Shannon rather, released a paper where he talked about trying to quantify information. And that may seem a bit confusing because how really can we quantify information? We know we can quantify weight. I know how much I weigh. I can measure that in kilograms, or I can measure that in pounds by standing on a scale. Or height. I can measure my height in inches, in feet, in centimeters, meters. Those are quantifiable units. But how can I measure information? Now, my mom continues and she goes on and says, your aunt has given birth. There were two ways that I could have possibly reacted to this. The first one being, I knew my auntie was pregnant and I knew she was bound to give birth. So that's a low level of information that my mom has passed across to me. I'm not very surprised. Or, secondly, my mommy could have gone ahead and said, she has given birth, but I didn't know that she was pregnant in the first place. So I'm very surprised. I'm taken aback. That's a high level of information or a high amount of information that's being passed across because it's something that's new to me. So basically, uh, surprise is how predictable or unpredictable a message is. That's what information is measured by, how predictable or unpredictable a message is, or its level of surprise. Um, Information theory says the more surprising a message is, the more information it carries, vice versa. So this is what Shannon Cloud, or Cloud Shannon rather, was trying to pass across to us in the 1940s. And this is basically what information theory is based on. So here we have the mathematical formula that he provided to us. First of all, we're using the logarithm in base 2 because in computers, we use binary, ones and zeros. We also have the negative sign here because remember we're dealing with probability. If we put any number between 0 and 1 in a logarithm base 2, it's going to give you a negative number. But we're trying to get a positive number because we're trying to quantify it. So that's why that negative sign is there, to cancel that out. Which takes us to our next slide, entropy, which we did see on the last slide. So uh, entropy can be defined as the amount of uncertainty or surprise that's in a source of information. So my mom continues. She says, your aunt has given birth. And she goes, guess how many children that your aunt has given birth to? So normally, I guess one, because that's the most common answer, right? And my mom goes, no. So I'm a bit surprised. I said, two? My mom says, no, still. So I'm a lot more taken aback. And she says, three. Or rather, I guess three. And she says, yes, my auntie has had triplets. And I'm taken aback entirely. Now, this table here shows three different outcomes of the births. Now let's take it to that. We're going to give birth to triplets at most, just hypothetically in this situation. So most births are just one baby, right? So we can see, based on this probability, 0.9.5, I say 95% of the time that there are single childbirths. Twins are a lot rarer than single childbirths, with 4.5% maybe. And then triplets, which are incredibly rare, just maybe like about 0.5%. So here's where information theory gets very interesting. The more unlikely an outcome, the more information it carries when it happens. Now, this is the mathematical formula that we were showing in the last slide. So we can see that with a probability of 0.95 out of 1, it only gave us a very low amount of information to work with, just 0.074, because that's a low amount of surprise. It's common. So the more common something is, the less information it carries. But then we go and take a look at the three babies that my auntie has in fact given birth to, and the probability is 0.05. And when we insert that into this formula, we get 7.64 bits of information, almost a whole byte. That's significantly larger than the single baby's information that was passed across. So the surprise or the information content of the three babies is very high. Yeah. So one baby gives about 0.07 bits, and that's hardly any information. So even though triplets are rare, they carry the biggest punch in terms of information because they are very surprising. And now this takes us to entropy. We did say that entropy is the average information in a set of outcomes. So now we have three sets of outcomes. My auntie had one baby, my auntie had two babies, or my auntie had three babies. Now, these are all their information when calculated. So to calculate their entropy, we do go ahead and multiply the probability by the information, and we can get the entropy. And when we all add all the entropy together, we get the average information, which is entropy. So that's how we can calculate entropy, and it's very simple, and it gets simpler over time. I'm sure you get a better grasp the more you do study it. So this carries us to the next slide. So now that we understand that information is about surprise and that entropy tells us on average how much information or how surprising or uncertain a message is, we go on to something else. It's one thing to have information, and it's another thing to send the information across. So when I was outside in the rain, I had very bad network, and I heard a message that was full of surprise. But then that also raised a question in me. Even with all this noise, all this static, all this disruption, and the bad signal, my mom's message and my message were still able to get across to each other, even with the unreliable connection. So that's where we move from what information is to how information travels. And for that, we look at the Shannon Cloud communication model. So here we have about five components, six, if yeah, about six components. The first one being me, the information source. So I'm the person that's sending or generating the message across to my mom. I want to tell my mom something, so I speak into my phone mic, and that's where I say hello. And now, my phone microphone is a transmitter or an encoder. It's going to transmit my audio signals, which are analog, into something digital, binary, that the computer can understand. After that, it carries it across a channel, which is the airwaves, to get to my phone and go over the mobile network that I'm using to make that call. And we also have what we call noise that's present in every day of our lives. So it's the rain in this scenario, it's the static, it's the weak network, the background noise, it's anything that distresses or distorts and interferes with the message. That's what we call noise. So the noise is in there and it travels with the message that I sent. So from the channel, it goes over to my mom's phone. That's the receiver or the decoder. So it carries my information and it converts the signal back into the audio to reach my mom, who is the final destination that can hear and interpret the message. That will allow us to move on to compression. Now, when I started realizing that my voice was breaking up as I was speaking to my mom, I started shouting and I repeated myself time and time again, hello, 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 so she would get the message that I'm sending across. This is called redundancy. It's repetition, saying the same thing more than once so that you can ensure that your message is being sent across the way that you intended for it to be. In information theory, it's called a trade off. So the more redundancy there is, the more space and time that's being wasted, and the less redundancy there is the possibility of the message getting lost. So this is how error detection and correction work. We are going to add extra patterns or clues to make sure that the message can be recovered, even if parts of it go missing. So that's why I keep on repeating myself to ensure that even if parts of my hello, hello, hello go missing, she can receive at least one of my hellos. Now, imagine I had to send this story to my friend on iMessage, for example, but was running really low on mobile data. So this was what I planned on sending initially. My auntie just had triplets. I'm so surprised. Triplets? But that's a lot of information being packed across, and it's kind of redundant because there's a simpler way that I can pass that same message across. I can say, Ants just had triplets with an emoji that shows that I'm shocked or surprised or I'm blown out of my mind. And it passes the same message across. Now, what I've done here is I've compressed that message. I've made it less redundant. Compression removes redundancy or predictable parts of a message or repeatable parts of a message so it can be sent with fewer bits, lesser information, and easier across the channel. So think zipped files or MP3s and JPEGs. Now, think about the voice messages you send across on Snapchat. Sometimes also the noise in the background is not captured. Why? Your phone is trying to reduce the amount of noise that's being sent across or over the channel so that less information is being sent across while the message is still being sent across. So the idea is the more predictable something is, the less space you need to represent it. So entropy will tell us the best compression possible that we can achieve, the theoretical limits at least, by using particular formulas. Now, this carries me on to noise, channel capacity, and error correction. So imagine the signal is really, really bad, and my mom is still on the line trying to communicate with me, but she can only say two words or two clear words per second before the information of the call cuts out. That's called channel capacity. It's the maximum rate at which we can transmit data or information reliably through a noisy channel. So if my mom tries to speak too fast, I'll lose parts of the information or the message. But if she speaks too slowly, it's going to take too long to get across to me. So we're going to ask, how much can a channel handle? That's channel capacity, and that's a very important concept in information theory. And how do we make sure that our messages stay within that limit? Shannon's theory also helps us to calculate this limit, and that's what really helps us to design a lot of the communication means that we have today, like the phones and the internet, to stay efficient. So later, my mom tries to send me a voice note because the phone call didn't really work out, but it glitches halfway. So I hear her say trip and let's. My brain basically is able to know that she meant to say triplets, even though I didn't hear it. That's my brain doing error correction. So digital systems do this with a lot of clever math, using error correction codes. Example, your phone. Assuming you're typing something to someone now and you say it's rain and G, that's not correct English, but your phone is going to correct that for you because it knows that you're trying to say it's raining. That's called error correction. So I know a bit of you, some of you may be wondering, so why are we removing redundancy just to add it again? Well, we do add some redundancy to make sure that it's not too little information that we're passing across, so nothing does get lost across the channel, like I explained in the previous slide. So all day I've been telling the story of one rainy phone call, but what we've been doing is unpacking how theory really does work in the real world, or unpacking building blocks in modern communication, or what really makes up modern communication now. That one call involved encoding, noise, surprise, redundancy, compression, channel capacity, error correction, and these are principles that power how we communicate with each other every day. So every time you send a voice note on Snapchat or an iMessage, it's compressed and sent over a noisy network, just like my call was with my mom. Or when you're watching Netflix and your mobile network is slow or your Wi-Fi network is slow and it's buggy, but you still see the stream as they intended for you to. That's using error correction to keep it smooth. And your Wi-Fi and your 5G or your 4G or your 3G that you use every day, those networks are built around information theory. It helps us know how much information can be pushed through per second. So even your Spotify that you use, the recommendations that you get from your Spotify or DNA sequencing, those use ideas from information theory to encode, transmit, basically decode meaning from all that data or information or sound waves. Even in AI or ChatGPT that we use so frequently today, it helps ChatGPT or AI ask better questions. So there's less possibilities or less there's less space for confusion or uncertainty. And of course, in this class, over this recording, there is information theory because this mic that I'm using to speak to you're hearing it decoded by your ears, interpreted by your brain, and all that is information theory too. So I hope I've been able to give you a great rundown of information theory, and I look forward to seeing you in CS 109. Bye.